Yeah, I mean, it's had advantages as well. We're working on, we just had a grant to look a bit further at the spring back of metal.
Yeah.
And we could have just like spent the same amount of money on some FEA software that was predicted to spring back.
Yeah.
But to us, it was more interesting to be able to model it in real time, basically. We don't want to wait 2 hours for a really good answer. We'd rather not wait any time for an okay answer, which gives us an indication of what we need to do to get a really good answer. So it's much more useful. So it's meant that because the particular way we model this is, I mean, basically break this up into lots of flat faces. So it's very coarse representation, but it means that we only have to do calculations on like tens of elements rather than tens of thousands of elements, which is finite element analysis. So we can do it in real time now.
Very impressive.
Have you ever done any of this with kids in school?
Well, I don't know how. Yeah, university students, nothing younger yet.
I can see 14-year-olds really loving it.
Oh, yeah.
Loving the paper stuff, right?
Yeah.
And then the question for me is, what could they then do with not very stiff metal? Because it would be just such a cool thing to do. I got this silly idea in my mind. They've got these Lego robots in school.
Yeah.
Could you program a Lego robot using
Sure.
Mindstorms to flip a piece of paper?
The first Robofold robots were Lego.
Really?
Of course. Not with Mindstorms, but
No.
they were just manually operated. But
Yeah, I just think there's a really interesting opportunity for.
yeah.
Because everybody's banging on about how daft the design technology curriculum is. That all they do is make key fobs. Which isn't true, but that's the kind of image.
Yeah.
But it does need some
This
serious.
is pretty instant in terms of
I mean, it
results.
is instant. I mean,
Yeah.
but it's quite sophisticated,
Yeah.
isn't it? And I
We've
think
done
that's-
workshops, quite varied ones. Some where we set like sort of engineering challenges, like make something structural, enclose something to protect it. So we give them some eggs and they have to throw it across the room and not break the eggs and all sorts of other things. So yeah, people making furniture, clothing, hats, rucksacks,
Yeah,
sorts of things. I mean, it's pretty extensive as well.
And how does the stiff, because you can often make things that are durable out of stiff card rather than metal, and that would be not cheap for schools.
Yeah.
So that's all a possibility.
Yeah, definitely.
Oh. I'll be in touch.
Have you looked at capturing human folding actions and pushing those into the robots?
Thought about it, yeah. Yeah.
Because I know there are, some robotics, work like that. You simply you record.
Yeah, you teach it.
So you could, I wondered if you could just record someone.
Yeah, we
from a
thought,
bit of paper.
well, we have these kind of big wooden robots which we built for one workshop, but they weren't really into high-tech stuff. So they were kind of doing that with their wooden robots. They had to test first, can it be made? They didn't want to actually make it with robots in the end, but we just said, well, you're going to have to just use these wooden ones to test those paths and see if you can actually reach all those positions with a robot. Do they clash or these other things?
So you had people manipulating things with the same geometry.
Yeah,
as
exactly.
robots.
Yeah, but
That's
it's half size or quarter size. But yeah, it's a nice way to. What I would like more and more is to be able to just translate those analog processes more directly. So we did stuff quite early on, 3D scanning these surfaces so they can be rebuilt for this sort of animation. We don't have those tools kind of available, but all of those sort of approaches where you can do something quickly, inaccurately by hand are so much more valuable than doing something really accurately with no particular reason or having to do them very slowly because they're really accurate. So it's much more valuable to do stuff many, many times very quickly early on in the design process. And yeah, if part of that means you can then directly translate that, it's great.
Have you thought about having a person as a controller for the robots? Like so they're directly controlling what the robots are doing.
Yeah.
So they,
We
so
had
they
some, like, one of the guys who work with, like, hooked up his Connect to our robot simulation software, so that you could say, like,
yeah.
I think it was like a sort of stick model, so if he moved his hand, the robot would.
Yeah. Do you try it with the folding actions or?
No, we didn't do that. We didn't hook it up to robot either. just in case. I mean, it's possible, but it's quite a big project, just purely for safety reasons. Like, you just have to be so sure that you're not going to if you're doing it in real time, there's more possibilities for error, and the consequences are greater. I mean, our robots, like, they can't hit anything because they're physically constrained to not hit our walls and stuff. They can hit each other, and you wouldn't go so close so they'd hit you, but you have to take a lot more into consideration than that. But we did some real-time stuff for the Sun newspaper where we had a web app which you control, like, power and accuracy of a robot, and then it hits a pinata. So that was all real-time, sending stuff from their server to a robot that hit it on the internet.
Yeah.
So you can do that, but it's a bit safer when it's a little mini robot and it's just a pinata, not these huge robots.
Have you thought about, do you know Unto This Last?
Yeah, I used to work there.
Okay. Of doing something similar with parameterized product lines that...
Yeah, we have. I mean, I've designed lots of products, but I haven't really got around to making them, strangely enough. I tend to get more into the technology and then doing consultancy for other people. So, but yeah, I think it's the same, and we've spoken to them about putting robots there and doing that on site, but we haven't got around to it yet. So if I get more time.
You've got a long to-do list.
Yeah, it's very long to do this.
Can you just show us the?
Yeah. So it hasn't been sanded on the edges, it's a bit sharp, but a little feel of it if you want. So that was quite a surprising piece because we just had two robots here and here, and the fixed robot here. But when we formed it, this curve didn't form here; it just sort of formed near it. So we were quite confused. So we had to sort of make sure everything was in the right position. But in the end, the material just wanted a form because of these different forces in a slightly different place. So we moved the curve just up a little bit, so it formed in exactly the same place to form this really sharp curve. But it essentially kind of didn't need us to score that line even. So it just wanted a crumple in its own way in a sort of controlled manner in that place.
If you decided to bend it all the way, would it snap, or what would this metal do if you decided to bend it on itself?
Well, no, it would just bend. Yes. So if I mean, there are certain ways it will fold and certain ways it won't fold. So, examples of that. So, and if you folded this way, like this doesn't really want to fold really that way again. It actually wants to fold this way now. So that folds nicely this way. But if I did this the other way around, then it doesn't fold. So it has certain kind of states where you wouldn't be able to fold it, or in this way you have to have this fold. There are things that are just not possible to fold there. Hence having to get hands-on to discover those things, because you might say, well, no, I'm imagining that it'll work, so it'll work, but it won't necessarily work.
Do you find much variation between batches and materials, different batches and materials?
Well, not enough that we would notice, because we don't measure it too finely. I mean, one of the interesting things about this process is that because we don't stretch the material, we don't change the surface area or anything, so we will drill all the holes, cut the edge shape before we make it. Conventional pressing, you do that afterwards because the material is flowing into the mould. So those material properties are really crucial for pressing. But for this, if it's not quite right, if we don't fold an angle exactly as we were expecting, if it's got to fix onto something, it's still going to fit perfectly because we haven't changed the surface area. So it just sort of pull itself into position. So it has some benefits there, which it's not quite so prone to changes in material batches or grain direction or anything.
Do you have control over the scoring, like the depth and the width of scoring to control?
Yeah.
How precise or how precise does that need to be?
It's plus or minus 0.2 mil. So we go in, that's 1.4 mil thick, so we'll go down to 0.7, and if it's above or below sort of 0.5, 0.9, then
So it's basically just the depth or also the width of the score?
mainly the depth, yeah. Because if it's, we can do width, like sort of flat bottoms tool, normally it's a V tool, but if we're sort of folding, unfolding the way it's better with flat bottom, the V tool can split the metal if you unfold it, because it's sort of got a V shape in there already.
No, your scoring is all on one side.
Yeah, so we can flip the sheet if we need to, but it's basically, we try and score it all on the back face, this face you won't see. So if we're doing laser cutting, we'd have lots of little scores in it, and you'd see it from both sides. But this means we can actually have a clean side to it, which you can touch it and something like that.
Do you stick with just one fold at a time? Like do you have pieces that have multiple fold, consecutive folds on them?
Yeah, so it does need to simultaneously fold, because if we have one, like if we start with these surfaces curved in this direction, and in order to get it to here, you have to kind of pop through that to get to here. So you have to literally change the curvature from being like this to being like this. And that tends to get quite difficult. So if I think it's extremely folded and try and put one of these folds in, I've just literally got to crumple that to get it there. So we don't want to crumple bits of metal to do that. So it does have to be simultaneous. Unless you've got something like that, which has got no relationship to anything around it, so I can just fold those one by one.
Yeah, but if you've got a fold over here that is independent of the fold over here, can you do both of them, or does?
Yeah, well, in the same way that like if I put a couple of flaps, like these are independent of each other, so we can fold. It doesn't matter when they get folded. Whereas this is basically the way we model it is as a linkage system, so it does everything moves simultaneously, and that's what the material wants to do. So we have to fold it all in one go.
So in between those folds, does the robots know where it is on the table, or do you have to put it in a specific place for it to?
Sure, yeah, it knows where it is.
Okay.
I mean, we don't tend to fold little things like this. Everything tends to be this kind of big simultaneous folding. But sure, if you folded this one and the sheet is on the table, then you can fold that one, whatever else you want to do.
Cool. Any more?